show that the Zarinsky-Murray interaction leads to an asymmetry in the magnum propagation. We do it by the Zarinsky-Murray interaction. And actually, this platinum layer that is here because of the spin-orbit coupling, this induces a strong Zarinsky-Murray interaction at this interface, and this breaks the symmetry of the system, stabilizing homochiral Nel domain walls. And why is that important? Because now if we run a current through the platinum layer, so we generate the spin currents, and these spin currents could couple to the magnetic elements in our system. And in particular with the domain walls, we can drive them at a fixed velocity depending on the chirality. You see here an example of just a magnetic element in which run a current through this layer. We exert a torque that has a chirality. And it's shown here as these domain walls have this chirality. Depending on whether the same chirality is applied or the opposite, essentially you control in which direction the domain walls are going to move. So what are the current limitations of these technologies? Essentially with ferromagnets, you have stray fields, and these stray fields stabilize the motion of the domain walls driven by charge currents. So one could think about preparing synthetic antiferromagnets in which you basically compensate the magnetic moments by two layers coupled antiferromagnetically, or you could work with ferrimagnets that have much smaller magnetic moment, and then what's happening is that the angular momentum compensation, so where you compensate the two layers, let's say, the system becomes more antiferromagnetic like the behavior, and this is what you can see with this black one curve, that basically the velocity could be higher than for the case that behaves more like antiferromagnetic like system. But another problem with these materials is that typically they exhibit a lot of disorder, and this also prevents the motion of domain walls at small driving currents. So in this, as we said before, so we have, for instance, rated magnetic insulating garnets, which could be very useful for this type of technology because they could enable new functionalities, but also it has been shown that you can exert large torques in materials like thulium iron garnet, which exhibits perpendicular magnetic anisotropy. As we said, we would like to have perpendicular magnetic anisotropy, and we can exert torques and actually switch the magnetization. See, this could be good material, good candidate for driving domain walls, because also these materials are, you can grow with a single crystal like, and then you have a much small concentration, you have a more concentration of defects in the system, so you could eventually get much higher velocities. So how we prepared our devices, so we basically took a substituted scandium substituted gadolinium gallium garnet substrate, and we put on top, so we grow by pulse laser deposition, a thulium iron garnet film, and then in situ we deposit platinum. And then we went to the clean room, we patterned this platinum layer in the form of a whole bar shaped racetrack, and the first thing that we did was to characterize the magnetic anisotropy of the system by measuring the resistance, the whole resistance, whole response while applying a charge current. So this is based on the spin Hall magnetoresistance effect, and in short, what's happening is that you have resistance that resistance response that depends on the orientation of the magnetic moments, and here we see that we find a square-like hysteresis loop when we sweep the magnetic field out of plane. So we confirmed that we have perpendicular magnetic anisotropy, and then the next thing we did was whether we can manipulate the magnetization of this layer by applying a charge current with large current density. And if we now apply a magnetic field in plane, and this is important because we need to break the symmetry of the system to stabilize one final state over the other. So when we apply a small magnetic field in plane, so in positive in the current parallel to the current as shown here, what's happening is that the negative current pulses, we stabilize down magnetization, and eventually when we sweep up the current pulse, we can switch the magnetization from down to up. And if we now apply the magnetic field in plane opposite, so we stabilize the opposite magnetic state. And this is just a reason for the symmetry of the torques in the system, and basically the idea is that we can stabilize up magnetization when both the current and the magnetic field are parallel, and down magnetization when they are anti-parallel. So the question is how this switching occurs in the system, and for this we employed optical imaging, and basically with polar sensitivity, with MOC with polar sensitivity, we first saturate down the film, then we apply a positive charge current, and then we see that this region switches from down to up. And we can see that we can locally control the magnetization because this is a continuous thulium iron garnet layer. So here we have thulium iron garnet, but we can control locally the magnetization underneath the current line. So now, as we said before, so we need a particular spin texture for the domain walls to be able to drive these domain walls via electric currents in this type of heterostructures. For knowing how the spin structure of the domain wall is, we employed nitrogen vacancy magnetometry, which is based on a nitrogen vacancy center placed at the tip of the apex of a diamond made AFM tip. And then by scanning this tip over the surface, we can map out the stray fields. That's actually what you get. So for this is the domain wall sketch here, and we have the domain wall. We can map the stray fields, and we have a region that is partially covered with platinum and regions that are not covered with platinum. And then we can, by analyzing how is the strength of the stray field, we can infer whether we have left-handed nail, right-handed nail, or a block type domain wall. And we saw that on the region that there is no platinum, we stabilize left-handed nail chirality, and then even the position of platinum. So in the region that we have some platinum, so we have a partial quenching of the AMI, and this is because we have a negative AMI from the substrate and a positive AMI from the platinum on top. So then the last thing we did was to drive these domain walls by applying charge currents, and sketch it here. So we can apply a pulse, and then we drive the domain wall from left to right, and from analyzing the displacement that we get with the pulse, we can extract the velocity. And by sweeping so tuning the field that we apply in the plane, we get a linear trend that we can linearly change the domain wall velocity. And by comparing the different the different directions of the current and the field, so we have a shift here that is related to the AMI that we have in our system. As I said, we have a partial quenching of the AMI because of the heterostructure, because the substrate and the top layer were partially canceling each other. But still, we have a certain AMI that favors this domain wall type. So, or this for this configuration of the field to drive the domain walls much faster than for the other configuration. That's why we have here a shift. So we can control the velocity of the domain walls by magnetic field and current. And we see that we can drive also domain walls very high velocities with the current density. So these have mobilities that are comparable to the ones that you may get with metallic layers. So with this, I would like to talk about it for a few minutes if I have time. Maybe 2 minutes. And essentially, when we apply current on a heavy metal, so when we generate the spin currents, and with the spin currents, we can again generate magnons. Now, if the magnetization are parallel to the spins, and provided that we have some thermal fluctuations, we can also excite magnons or annihilate magnons. So essentially, now if you put these platinum layers on top of the magnetic insulator, you can generate magnons in the material, and then these magnons propagate away, and you can detect them in a second platinum layer. You can absorb these magnons, convert in spin, a reciprocal process, spin to charge conversion. So you can actually transform these magnons in electrical signals in the system. Essentially, what's happening is that we fabricate a device like you run a current here, and then you measure the resistance in this stripe, and you see these filters when you rotate the magnetic field in the plane. So because we need the magnetization to be perpendicular to the current to have a signal, and we have zero signal when they are parallel. Then the question is, because we have DMI as we have seen before. So the question is that when in the presence of DMI, we have an asymmetric propagation of the magnons in the system. So this was shown in this work, and actually this was shown first in metals, and and then in also in yttrium iron garnet, that you can induce an asymmetric propagation of magnons. So we fabricated this type of device and then measured the magnon transport in the system, the electronic magnon transport, and so that we can modulate the dispersion of the magnon bands by an additional term that corresponds to the DMI in the system. Essentially, this is what we get in the measurements, and we see this asymmetric propagation. We can infer the symmetric propagation by measuring on the right and left detectors, and this is the contribution that we get, and this is let's say the analytical formula that you would expect to have. Here are solid lines, and then we see that we can change the domain, the propagation of the magnons, so the propagation length, so the characteristic length which the magnons can propagate by a few percent, depending on the DMI, which we can tune by the thickness of the material, because it's an interfacial DMI, and then it's a larger the effect, the thinner is the yttrium iron garnet film. So with this, I would like to conclude saying that we can control the local magnetization in extended films of thulium iron garnet, which could be interesting for magnetic applications, and also we saw that we can induce interfacial DMI. In particular, the substrate interface is the one that dominates in these. So in oxide-oxide interfaces, the one that dominates the interfacial DMI in these systems. And also show that we can drive domain walls at high speed in this type of functional devices. And also because of the DMI that we induce in this type of materials, we can also make a magnon devices in which we can control the magnon propagation depending on whether we have right or left detectors. And this is a way to induce drift currents similar to what you could have in electronic systems with electric fields. And with this, I would like to thank all the people that contributed to this work and you for your attention.
Thank you very much, speaker, for an interesting presentation.